Yeah, dear students, welcome to the visualization lecture. This year, an online lecture. I try to cover the topics that are always part of the visualization lecture. Want to introduce myself first and this topic, visualization from a computer science point of view. I will explain how this relates to other lectures that we have, like computer graphics and information visualization and visual analytics, to explain to you where this fits in the overall curriculum. Um, I will give the lecture and will prepare all these lecture videos. Gabriel Mistelbauer, Benjamin Behrendt, and Benedikt Meyer will support me and provide the exercise. All of them are experienced and did this already last year. The major goal of the exercise will be to make you familiar with many visualization techniques, to give you an opportunity to try out many things yourself, and you will primarily use the tool D3 for this. I have included here the information on mail addresses and telephone numbers for Gabriel, Ben, and Benedikt. You also see here the link to the LSF entry where this lecture and the formal requirements are described. Let me briefly introduce myself. I have studied here also at the computer science faculty in Magdeburg, computer science between 1989 and 1994. Became Diplom-Informatiker, as this is called, and then did my PhD research also here at this university in the computer graphics research group, dealing with some aspects of interactive visualization and from the application point of view with anatomy education. I then left the university and worked for an independent research institute in Bremen, MEVIS Research. MEVIS stands for Medical Visualization. So that was an institute that is very application oriented. That means we never initiated any project where it was not from the beginning very clear which physicians, radiologists, surgeons, or other physicians are interested in this research. I myself was the head of the liver surgery planning group, so we developed computer-assisted tools in order to support surgeons to plan complex surgical interventions on the liver. That finished in 2003, and since then I'm back in Magdeburg and lead the visualization research group. I included here the URL of our website where you find all teaching related information, but also all research oriented information. This lecture, visualization, I created in 2003 and have modified it many times in the meantime in order to consider recent trends and developments. The research focus of my own activities and also of the whole group is on interactive 3D visualization. We primarily research medical visualizations. That means, like in my previous job in Bremen, we try to address physicians, epidemiologists, neurologists, and others, and want to develop solutions that really fit in their workflows. In recent years, we are interested more and more also in visual analytics. That is a combination of visualization and analytics, machine learning, clustering, outlier detection and other things. And in medicine, this is particularly interested if you have large databases about patients, where you know a lot about their state, about diseases that may occur, and can use this visual analytics type of research, for example, in order to identify risk factors for diseases, which of course would be essential for developing preventive measures. And the second large branch of our research is virtual reality. So we started to investigate more and more how can we support tasks like surgical planning or medical education with immersive VR solutions. That will not be part of this lecture here, but just to make you aware of this, and of course there are opportunities to carry out a bachelor thesis, a master thesis or things like this in this virtual reality type of research. Yeah, at the beginning of a lecture, it should be clear what are the requirements, what do I expect from you. Um, you should have an understanding of algorithms and data structures, like provided here in the lecture, algorithms and data structures. It is not necessarily that you have exactly heard this lecture, but you should have an understanding of algorithms and data structures, when a problem can be solved with an algorithm at all, how to think about the complexity of an algorithm, um, some numerical considerations that should be somehow familiar to you. It is also at least desirable, I would not say required, that you have an understanding of computer graphics, of rendering. Computer graphics is a very related discipline to visualization, strongly related. Basically, we can say that in visualization, we use the techniques from computer graphics in order to create the final images. Visualization involves many more steps. We have to think about which graphics primitives to use, which visual representations to use. There are design aspects involved, but at the end, yeah, we need rendered images, and that is the contribution of computer graphics. I carefully revised the lecture in such a way that it is not really necessary to know a lot about illumination models, textures, or things like this. But if you have an understanding of computer graphics, that would be a background that could be helpful at some points. Yeah, what are related lectures? So once you have heard the visualization lecture, ideally passed the visualization exam, what additional lectures you can hear then, and what could be interesting for you? Holger Teissel's group, the Visual Computing Group, provides a lecture on computer-aided geometric design, yeah, and that is related to visualization. Another lecture is Geometrische Datenstrukturen from Stefan Schirrer. So that is, yeah, from an algorithmic and theoretical point of view, a look on data structures that are useful also in visualization. So therefore, that is also related. Steffen Oelze-Jaffra, who worked in our group for many years and now leads an independent research group at the University Hospital, provides a lecture on information visualization. Information visualization is also a considerable portion of the visualization lecture, but nevertheless, Steffen can extend this considerably with his lecture, where he has 14 weeks time to explain basic and advanced concepts in information visualization, whereas I use only 3 of them, basically to give an introduction and to prepare you for this lecture. Another lecture that could be interesting for you, and that is also an English lecture, is on visual analytics that will take place in the summer term. Again, visual analytics, as I very briefly mentioned already, is a combination of visualization, interactive visualization, with data analytics involving topics like outlier removal, classification, computation of decision trees, and others. And it recognizes that there are at least 2 ways to analyze large and complex data. One is to provide good visual overviews and interactive visualizations. That is the topic here of this lecture. And the second is to use data mining techniques. Data mining may produce the very important results, but often they have a kind of a black box character. You do not exactly know how they come to a certain result, and visualization can help there in order to make this part of an interactive reasoning process, and that is what is called visual analytics. As I said, that will be described in a lecture in the summer term. And then there are more specialized visualizations. I said to you that the research focus of our group is medical visualization. So if you would be interested in doing a master thesis in our group, it would be really beneficial to take this subject. With Gabriel Mistelbauer, I have also a strong postdoc with really a long experience in developing medical visualization systems, for example, visualization systems that support in the diagnosis of vascular diseases, ja, Gefäßerkrankungen. Holger Teissel's research focus is flow and tensor visualization, so he provides a lecture that introduces in the special topics that his group is so specialized in and in fact even famous for. And there is a final lecture on mesh processing. Mesh processing is a little bit related to computer-aided geometric design. Yeah? Mesh processing is important in the car industry, for example, in manufacturing cars. So that these are the lectures that are related here in Magdeburg to the visualization lecture. At the end of the semester, there will be a written exam that will take 120 minutes and covers the lecture topics with a focus on the concepts. So I want to understand whether you know basic and some advanced visualization concepts and have an idea when to apply them, what they are good for, but also what are their limitations. It's not a kind of a programming exam. The requirements for being admitted to this exam is that you do the homeworks that you get in the exercises, at least 2/3 of them. You should complete and should be able to present in the exercise, which takes place virtually as well. Yeah, and if you want to finish this course with just Schein, yeah, you just want to have a certificate that you have done this. Then you need to fulfill the same requirements for being admitted to the exam, and you should pass the exam with whatever grade. Yeah, that are the requirements here to get a Schein. As I said, our web page has the URL www.wismd.de, and there you find a teaching category, and there you also find the specific information on this lecture, where we will also inform when the date for the exam, for example, will be specified. The access to the slides is available with user _student and password _lecture. And with the same access information, you can also get the information on the exercises. Yeah? So that is from an organizational point of view what I want to say. If there are any questions in a normal lecture, I would ask in this minute for such questions. Here this is not possible, so please write me an email. These things, of course, should be clear. Yeah, let me go a little bit more in detail and give you some hints and recommendations for books that may be useful or are indeed useful in order to complement just looking at lecture videos and looking at PowerPoint presentations. Yeah, it is always a more in-depth knowledge that you can acquire by looking in books, and maybe you do not read full books, but at least selected chapters where you deal with some topics in a bit more detail. There are a couple of books that I briefly want to introduce to you in the next minutes. I have emphasized two of them here with bold font, not because they are better than the others, but because they are ideally suited, in my opinion, to support an introductory course on visualization that is either in the beginning of a master program or at the end of a bachelor program. Yeah, these are the books from Tamara Manzner, Visualization, Analysis and Design, and the very recent book from Christian Tominski and Heidrun Schumann from Rostock University on interactive visual data analysis. Yeah. Here is also a list with even more extensive information. Both books that I have emphasized here are also available, of course only a limited number of them, in the library of the university, because I really want to recommend them. Yeah, let me go a little bit more in detail. Interactive visual analysis is a book that provides a very good general overview. Christian and Heidi are long-term visualization researchers, so you you feel that this is really a mature book, that they have their own experiences with all the topics that they describe. So that is really a very good introduction to visualization, and especially designed for teaching. Both of them have a lot of teaching experience in this area. In addition to many introductory topics, they also describe some advanced topics where they are specialized in from their research. So that involves in particular time-based visualization. Yeah, you may have data that changes over time, financial data, business data, data on COVID-19, for example. What are the temporal developments there? So such visualization techniques are described a bit more in detail. And what you also see here on the title page, graph and network visualizations, is another specialty of them. The second book is also a very recent book that's only a few months old, but it has a different character. It is a collection of chapters written by approximately 40 authors. Our group is also involved in this. That is not as coherent as a book would be that is only written by two authors, but it provides insights from many authors in foundations, mathematically foundations, other foundations from a computer science point of view, but also foundations related to empirical research, cognitive research. All these foundations are covered here. That is the result of a seminar that took place here in this nice monastery in southwest Germany, in the Saarland, where these 40 people met and discussed in breakout sessions individual topics, and then finally summarized their thoughts in this book. Yeah, let me explain a little bit more in detail the second book that I have emphasized on my overview slide on the literature, the book on visualization, analysis and design from Tamara Manzner. Tamara emphasizes, and that is even clear from the title, design aspects. Yeah? Design involves a careful understanding of requirements, of tasks that users have to solve. Yeah, she really carefully describes how you can derive a valid set of requirements, understand also the priority and importance of design requirements, and then go on after characterizing the domain and the requirements with visualization design, in the sense of developing prototypes, early prototypes that can be used for testing. Yeah, a design approach always involves a lot of contact to users, early testing in order to refine your visualization design and make it better. Like the book from Tominski and Schumann, it is not a book where you can expect visualization algorithms to be described. Yeah? They go not to this level of detail. They both are on the level of describing available visualization techniques, their applications, possible combinations, and limitations as well. So that gives you a broad understanding of what is available in visualization and how it can be used, but it does not provide you with details how to realize such solutions. Yeah? So that is what may be said about this book. The second book on this slide from Matt Ward and George Grünstein and Daniel Keim, that is a more in-depth discussion of data visualization that involves also algorithms and yeah, implementation strategies. Yeah? So that is how this can complement. Yeah, finally there is the book from Alex Telea, that is a visualization researcher also with long experience, meanwhile originally from Romania, but he works since more than 2 decades in the Netherlands, Groningen and Eindhoven. And that is already the second edition of his book, also dedicated to teaching. It is an in-depth discussion, yeah, which goes more into details and algorithms. And a little bit you can also from the title page recognize where it has a focus, namely that is on graph visualization, and in particularly also on software visualization. Yeah? Software visualization deals with giving an overview on large software projects so that a software developer gets aware of class dependencies, for example. There are different relations, not only inheritance relations in an object-oriented programming. That all can be shown quite well with graph and network-based visualization. That is one, not the only, but one focus of this general book. Yeah, and then let me briefly say a few words on our book that I co-authored together with Charles Botha in 2014. As the title suggests, it is focused on medical applications in diagnosis, treatment, planning, and medical education, but it also has some aspects that are quite general and that are also part of this lecture here, namely how to visualize three-dimensional data with surface visualization, with direct volume rendering, also with which interaction techniques are useful in order to explore such complex three-dimensional visualizations, for example, with using clipping planes or other cutting facilities to provide an inside view in some structures where otherwise you would only see external surfaces. Yeah? So that is for the book Visual Computing for Medicine. Yeah, what you can learn in this lecture, what you can expect. I want to come a little bit more to the actual content of the lecture. You will learn about fundamentals of the human visual perception system and its influence on visualization techniques. So my goal is not to explain to you whatever I have learned on perception, but I want to be very precise in explaining how some perceptual theories and even laws are related to visualization design. Yeah? So that is one essential parameter for successful visualization design. Then we will discuss basic visualization techniques, which includes, for example, how color is used in visualization. Some people without a good understanding of visualization think that visualization only means to select the right colors for a visualization. Yeah, that is of course not true. Visualization is much more than this. But one thing is true, the selection of colors is really an important part of visualization design. There are other techniques that are frequently used. ISO lines, for example, I would consider as a basic technique. You see them in every weather map, for example, also in many geographic maps. So this will be explained. And some advanced techniques, I will not go in all details of volume rendering, but I want to convey a basic understanding of general approaches to volume rendering and show you results and some acceleration strategies, because large data are involved, and whenever you have to process large data, even with the powerful hardware that we have today, you should also think about making this as efficient as possible. Yeah, and vector visualization is a final example. I said in the beginning it would be desirable if you have some background in computer graphics. Yeah. On the other hand, I would say with this lecture here on visualization, you would also enhance your knowledge of computer graphics. So for example, I will describe some spatial data structure and also describe how polygonal meshes are handled and processed. We will discuss topics like mesh smoothing that could also be considered an advanced computer graphics topic. One type of visualization I have increasingly considered in the lecture are large and abstract data as they occur in business and finance, but also in some scientific areas like climate research, and that leads to what is often called information visualization. Yeah? So I started with one lecture on information visualization, and meanwhile there are 3 slide sets on information visualization, and typically I need more than 3 lectures in order to cover all this information that I consider at least a substantial introduction in information visualization. I mentioned that Steffen Oelze-Jaffra provides a separate lecture on information visualization, so that is optional for you, but you should have at least a solid introduction in this area. I also want to explain how to design visualizations for specific users and tasks. I cannot go into detail there and can only mention very selected users and tasks, but I want to convey this understanding that visualization needs an understanding of a certain domain and of certain users that have some qualifications and expectations that may be familiar with many conventions from their daily work, and it is important to understand this for you if you design visualization solutions. Yeah, let me describe some citations and definitions with respect to visualization. Before I do this, I would mention that the term visualization is very widely used, not only in computer science. Yeah? So people may tell you that they are doing visualization, and you will understand a few minutes later that they do not have something in mind that is related to computer science. Visualization is a term that is used, for example, in psychotherapy, or more general in cognition research, in order to describe the phenomenon that people should imagine, very clearly imagine their goals, their perspectives, what they want to achieve, for example. That is what they call visualization. Yeah? They tell you, for example, if you want to learn something and you want to remember something, try to develop a visual representation of numbers, for example. Then it is easier to remember them. So that is what they call visualization. A radiologist would also use the term visualization, and he uses this term when he applies a contrast agent that is injected in the venous system, in vascular structures, in order to emphasize some structures, typically vascular structures. Yeah? And then he would say, by using this contrast agent, I have visualized some structures. And another use of visualization is in biology and physics, where people spend a lot of effort in order to discriminate different tissue types, for example, in microscopy images. Yeah? They develop very special techniques to discriminate structures with different colors. And they would say, with this we have visualized some phenomena. All this is what we do not mean here. Yeah? We have a computer science view of visualization. Let me start with a citation from Hamming. The purpose of computing is insight and not numbers. Yeah? That is not a definition of visualization, but it explains that just to have a lot of numerical information and provide statistical analysis, that is probably often not enough to give users an insight in the data. Michael Friendly is a person I would refer to as a graphical statistician. Yeah? So he has primarily an education in statistics, but he uses graphics, statistical graphics as he would call it, in order to enhance the understanding of the data, in the sense of Hamming. Yeah? The purpose is not numbers. And he states, like, good writing, good graphical displays of data communicate ideas with clarity, precision, and efficiency. So that emphasizes the potential of visualization, but on the other hand, visualization can also be misleading. Sometimes it is deliberately used to mislead users because images are so convincing. If I create an image that leads to a wrong impression of the data, that may have a strong influence on the thinking of that person. There is even a whole book that is primarily full of examples from cartography that is entitled How to Lie with Visualization. Yeah? How you can systematically deviate the impression that a viewer has from an image with visualizations that are misleading. They are not wrong in the sense that data is altered before it is visualized, but the way it is visualized could be misleading. Yeah? Yeah, and finally, a definition from Gita Dumik: a computer-generated image using a computer representation of data as primary source. A computer representation of data. Yeah, that's the difference to other uses of the word visualization, and a human as its primary target. That means a computer-generated visualization is really designed in such a way that a human can understand it as good as possible. Yeah, let me give some more information on visualization and some more definition. I want to say a little bit more about this publication from McCormack in a minute. Here I only want to use his citation. Visualization is a method of computing. It transforms the symbolic into the geometric, enabling researchers to observe their simulations and computations. Visualization enriches the process of scientific discovery and fosters profound and unexpected insights. Yeah? That contains a lot of wisdom and interesting information. It transforms the symbolic into the geometric. What could be the symbolic? For example, it could be a database, yeah? A large table with many numbers on a certain phenomenon. And that is translated into the geometric, into something that you can view, that you can perceive, where certain shapes are used and colors are used. I would say from today's perspective, here the focus is strongly on scientific discovery, on researchers. Visualization currently is not only used for visualization research, but if you look in Spiegel Online or in the New York Times, for example, there are quite sophisticated visualizations and that are aiming at laypersons. Yeah? So visualizations are used more broadly. Visualization for the masses is a topic that we often discuss, how we can create visualizations that are not too complex for a few researchers only, but can be used more broadly. Yeah? And later, also from an important book, is a citation from Aref, Charles, and Elvis. When computer graphics is applied to scientific data for purposes of gaining insight, testing hypotheses, we speak of scientific visualization. Yeah? Hypothesis testing, that is primarily the domain of people in statistics. Yeah? And with certain confidence, they can reject a hypothesis or confirm a hypothesis. In a similar way, also visualization can contribute to testing hypotheses. Yeah? Gaining insight is mentioned again. So we want to explore large data. We want to understand, are there connections between certain data that we have collected there? Is there perhaps a strong correlation between them? And if there is a strong correlation, is this also something where there is a causal relation? So one thing really is the reason for another thing. Yeah, that is the kind of thinking that can be supported very well with appropriate visualizations. Yeah, let me briefly describe the history of visualization, as I want to call it. Yeah, I want to be very brief here. I know as a student I was always bored if people started to talk about history. Yeah, I started here with mentioning some developments that are obviously much older than the computer. So that is not computer visualization, but it makes you aware of the fact that computer-generated visualizations have their roots in other disciplines like astronomy, cartography, and others, where, for example, maps have been used extensively to support a kind of spatial thinking. Yeah? Why is spatial thinking important? If something happened close to another place, then the likelihood that it is related to this development is quite large. Yeah? And it is not so large if it is more far away. A map display can easily show such relations. Yeah? Tycho Brahe and Johann Bayer created maps to summarize their observations in the sky. Yeah? René Descartes, that was a French mathematician, said visualization, and in particular the use of diagrams, has a crucial part to play in scientific investigation. Yeah? So that was clear to him already in the 17th century. Some visualization techniques that we use extensively today, like height fields and isolines, were used for the first time by Edmund Halley and later by Alexander von Humboldt, yeah, in combination with geographic maps, for example, but also to show variations of temperature and magnetic field strength. So I make a big step to the 20th century, and the last developments indeed are related to a computer science view of visualization. The SAGE system is often, yeah, characterized as the first substantial visualization system. It has a military origin. It was for aerial surveillance. The US is leading in research and visualization and computer science in general, and there a lot of research is sponsored by the Department of Defense, so it has military purpose. But despite of this, it is quite interesting to understand which techniques they developed, how they combined them to a quite large system already in the 1950s. Jacques Perdin is a cartographer, yeah, a French cartographer, and he wrote a textbook first in French and later it was translated to English and became very popular, where he described visualization variables, general visualization techniques that can be used to show data of different type. We may have numerical data, that is data in a certain range, it is continuous, but we may also have nominal data, that is, for example, whether a car is manufactured in Germany or in France or another country, that is not numerical data, but also there we have differences that should be obvious in the visualization. And he explained which visual variables are appropriate for which type of data. And that is based on really a lot of experience, and his experiences that he described there are mostly still valid today. And then there was the report of McCormack, DeFanti, and Brown. I mentioned the term, the name McCormack a few minutes before, together with the citation, what visualization is about. So that definition of visualization was part of this report. That was a very strong activity. I would refer to it as self-reflection of scientists working in a certain area in order to describe what should be done in the future, what are interesting perspectives, how we can go on with a discipline that is called visualization in scientific computing. Today, this is considered as the hour of birth for visualization. Yeah? This term was not familiar so far. Computer graphics existed earlier, but scientific visualization is basically the result of this report. And that has had a lot of consequences for research funding in the US that was focused on certain areas described in this report, and it's structured also in a way as it was described there. Yeah, the more recent history, yeah, scientific discipline needs conferences, it needs journals, yeah, ways how researchers publish their results and exchange with each other. So since 1988, that started, I think the first IEEE visualization conference, that's the leading conference, was in 1990. I think the IEEE Transactions on Visualization and Graphics, that is the leading journal, started in 1995. There was a book from Edward Tufte on envisioning information in 1990, which was also quite influential. I have not included in my list of recommended books because most of these things are meanwhile updated and brought in a more current context in the other books. I mentioned several times the term visual analytics that started to become popular in 2004 and 2005 and led to the start of the IEEE Visual Analytics Science and Technology Symposium, VAST it is abbreviated, in 2006, so that takes place for the 15th time in 2 weeks. And yeah, the most recent development in this area, as I would call it, is LDAV. LDAV stands for Large Data Visualization and Analysis. So it considers challenging applications where really large data is involved. Yeah, for example, with millions of points in time or billions of spatial points, where a lot of data is measured or simulated and needs to be displayed. And from a computer science perspective, this leads to the necessity to develop efficient solutions, um, efficient in terms also of memory consumption, efficient by using graphics hardware or by parallelization or combining a number of these strategies. And finally, I want to mention visualization software, general visualization software, not for a particular application area, because only with this general visualization software, many people can use visualization, can create visualization solutions, not only people with a PhD in visualization research, but also a broader, broader spectrum of computer science experts. The first visualization software was AVS, stands for a visualization system, was developed in 1989. Later, Silicon Graphics was a graphics manufacturer, a vendor of graphics workstations, and they also provided the software, of course, to use their really brilliant hardware. And the Iris Explorer was their system developed for visualization. I think even more important is the visualization toolkit, because that was platform independent. The Iris Explorer was bound to the Silicon Graphics hardware. The visualization toolkit from Bill Lorenzen and colleagues is a very nice piece of software. You can really learn a lot about visualization by understanding this hierarchy of classes, these dependencies, and by using VTK. Not all VTK solutions are very efficient in the sense of LDAF, that you can process really large amounts of data highly effectively, but you understand VTK code very well. That is my impression. Tableau is a system for information visualization and also for visual analytics. Tableau is meanwhile 17 years old, a quite successful commercial solution. So if I would speculate, if some of you later will really work in the visualization area, it is very likely that they will use the Tableau system. And the second system where it is very likely that they may use it is D3, that is even more recent. I think it's from 2010. It provides many visualization techniques, so they are available. You can use them, combine them, parameterize them, and that is all available in the web. So you can create solutions where you can say to your cooperation partner, you just need to open your web browser, and I give you a special URL. You need not to install any software. So for cooperation, that is really a huge advantage, and it explains why D3 is so popular. And because D3 is so popular, and we also have a lot of experience in our group with using D3, in particular for visual analytics types of applications, we use it also in the exercise quite extensively. So you will get familiar with D3 as well. I mentioned already this report from McCormack, DeFanti, and Brown, Visualization in Scientific Computing, as part of the history. Now I want to mention some crucial points of that reports. They envisioned that computer-supported experiments may replace real experiments which are either too expensive or too dangerous or even completely impossible to carry out. So a current trend, for example, is to replace animal experiments whenever possible. It will not be possible to replace them completely in the near future, or at least we will lose scientific discoveries when we would do this, but the number of animal experiments can be reduced strongly. That is important for drug development, for example. What has been done in the years in between this report and now is, for example, to create many computer-generated solutions for testing, for making experiments in the car industry, in the car development. Yeah? Many aspects of this development where in earlier times you built a prototype, a physical prototype, and tested something and measured something with this physical prototype can now be realized based on a geometric prototype in the computer with simulation of the underlying physics and visualization of the results. Another crucial point of their report was that the amount of data is huge. Data in various temporal and spatial resolution occurs. It will be heterogeneous, that means there are different types of data, binary data, data with very low ranges where you only have a few possible values, and then numerical data with a large range of continuous values. They also envisioned that even if you are very careful about data quality, often you have data that is not complete. Yeah? You have partially incomplete data and you have to get along with it. The analysis of simulation experiments requires dedicated visualization techniques. So they formulated as goals to develop appropriate hardware, algorithms, software systems. They were very clear about the fact that standards are needed for the exchange of data. Yeah? Otherwise, you spend just a lot of effort in order to import many different formats. They were also very clear that many solutions will require parallelization and such, therefore, networked solutions are important. So, and then there was another very strong initiative 70 years later. Again, I would summarize it as a kind of self-reflection. Where are we in our field, scientific visualization? What could we achieve? What should have priority? How we can also serve other disciplines in an ideal manner with appropriate research. That article was written by Chris Johnson, entitled Top Scientific Visualization Research Problems. And I mentioned some of the points that he has identified. Maybe one should say 2 sentences about Chris Johnson. He was at that time and for a long time the director of the Ski Institute in Utah that was worldwide the leading institute for scientific visualization. Yeah? And of course, he as a director has to think about what are our future plans with our large staff in the institute in Utah. But he did this in a way that it is more general and useful also for many others. Let me comment on some of the things here. Think about the underlying science. That means think about underlying methods, algorithms, about general principles. Quantify effectiveness of new techniques. That is something that really gained a lot of importance in recent years. It is often not too difficult to develop a new techniques for a certain problem. Yeah? You can imagine after 30 years of visualization research, for basically every visualization problems, we have a large collection of possible techniques. If you come up with another new technique, probably that will not be taken seriously and ignored unless you can show that your new technique is somehow better than existing techniques. Yeah? So that means you need to quantify this. Yeah? Can your users for particular tasks solve a task better than before? Are they faster than before? Or is the kind of reasoning process they make more accurate than before? Do they make fewer errors? That all is meant with quantify effectiveness of new techniques, and it's really important. I also want to comment on this one, represent error and uncertainty. I already mentioned that data is never perfect. It is, even if it is perfect, it has only a limited accuracy. A lot of data is acquired with sensors, and these have some, it's often called measurement noise. So if I have a measured value of 7, for example, I know the true value must be somewhere in this area. I can imagine a probability distribution. perhaps a Gaussian distribution that would characterize the likelihood for the different values, centered around my measured values, but with a certain standard deviation. And if I have many algorithmic steps where data is interpolated and rounded and otherwise processed, then typically this error is aggravated. A cumulative error results. That could be quite considerable. So we need to take this into account. Is our data reliable or not? Is it accurate or not? And if we process it, what happens to the limited accuracy that we already had in the input data? And actually in the effect, we should create visualizations that not only show data, but also the underlying uncertainty to avoid wrong conclusions and to support decision-making processes. And let me also comment briefly on this aspect. Consider perceptual issues. With this, I mean that a lot is known about how people perceive colors and contrast, how sharp they can see in certain areas of the visual field, not in the whole visual field, how they use this information for interpretation of spatial scenes, spatial configurations, and this knowledge should be incorporated in visualization systems. Therefore, I prepared one lecture for this topic. And there are other terms and techniques that I do not want to describe in detail. Time-dependent visualization he considers as something important. Often it is essential to look at data not only at one point in time as a snapshot, but to understand a certain development which may enable you to recognize some features like periodicity in time-dependent data, which then would enable you to predict the further development. So that was also considered as one of the important topics. The visualization pipeline is an important conceptual achievement in order to summarize and structure visualization. We start with data which we have simulated or measured or observed. We prepare them, we filter them. Maybe we are only interested in a subset of the data, or maybe filtering is applied in the sense of image processing and signal processing. We denoise the data, for example. So then we have more interesting and better data. And the most important part of visualization is the mapping step. Once we have this filtered data, we think about which graphical primitives we use in order to display it. Should we use color? Should we use certain shapes, symbols, isolines, or combine them? That is the mapping step. And then, with all the techniques that are part of the computer graphics lecture, these graphics primitives are rendered. If this is a kind of 3D representation, then you need projection, illumination, shading, and so on to create final images. So mapping means data is encoded with certain visualization parameters like colors or opacity, that's often quite important, or certain structures. Applications are really huge meanwhile. Climate research become more and more important, and visualization of climate data, not only for researchers but also for the general public, is important. In business, for example, visualizations of stock prices and other variables related to company information is important. Flow simulation is used in different areas. Other kinds of discrete simulations and also visualization of medical or geographic data is quite important. Early visualization research focused on expressive static visualizations. And while this is definitely important, I want to emphasize at many points in the lecture that we are not aiming only at static visualizations that are somehow nice and expressive in the sense that they convey the data very good, but that we need interaction, and we have to think about how to interact with the data. In general, data typically is too large to be displayed at once, so that all questions that you may have are answered by just looking at one visualization. You need interaction. You may be interested in a different portion of the data. Yeah, that's called panning. Yeah, if you move around a map display, for example, you zoom in into certain details and you want to expect that more detail is presented and not only an enlarged visualization. Yeah, that leads to zoomable user interfaces. Something that is basically inherited from cartography is to think about the data that you want to visualize in certain layers. Yeah? A cartographic map is generated by having a base layer and then adding some other layers. Not all other layers that are available, that would create visual clutter, too much information that you cannot perceive. But for example, you want to overlay a street layer. Or you want to overlay a layer that tells you about the railway connections. Yeah? So that you see them in connection with the topographic information. Another kind of interaction is filtering, which means that you select relevant attributes and ranges. Yeah? These are queries, as you know them from databases. Here in visualization, we typically have visual queries. We may have range sliders, for example, that provide a graphical representation as a basis for filtering. We may want to emphasize certain structures. Yeah? They were already displayed before, but they should be emphasized in order to be better recognizable. So that's another kind of interaction that's very frequently used. Tooltips could be very useful. Quantitative information for a selected object is shown when I go with the mouse over it. Labels and measurements, for example. Yeah? Symbolic information that may add to the visual information to better support the interpretation of the data. Yeah. So my major message here is visualization is a process and not only a final result. Users are actively involved in this process. They are responsible for doing this, and interaction techniques should be designed in such a way that they are really able to do this. Yeah, interaction provides the necessary flexibility. They allow it to tailor a visualization to the needs and interest of a particular user. Yeah? But for complex data and complex systems, even the interaction that a single user applies to the data may not be sufficient to fully understand the data. Yeah? There are possible strategies for these situations as well, like pair analytics, where actually a visualization expert and a domain expert analyze the data together. And the domain expert may say to the visualization expert, try to highlight particular data, try to show me whether there is a relation between this attribute and this attribute. And it is the visualization expert who actually carries out the interactions. The visualization expert learns more and more about the domain also, so she might make suggestions to the domain expert, the cartographer, for example, or the physician. Maybe you are also interested in this or that, then I could show you this or that in the following way to you. Yeah? So that is what is called pair analytics, and I think that's quite promising. It requires that visualization systems are designed in such a way that this cooperation is also supported. For example, there could be different input devices for different users. And guidance is another essential strategy, which means that instead of just providing a very large and flexible system where the users can do everything, but he does not know what to do, he gets support often based on certain workflows that have been identified. Yeah? They may get hints, they may get suggestions, parameters may be adapted to the particular data and used as default values. Yeah? So guidance not in the sense that the user is not allowed to do many things, but he gets some support to follow a certain path which has shown to be quite effective in the past. Let me comment also a bit on the disciplines that are involved in visualization. Visualization researchers often have a degree in physics or math, and that means they have a lot of understanding of math. Yeah? And indeed, that is quite helpful for visualization. Not at the level as we discuss it here in this introductory lecture, but for doing more advanced visualization, research and development, mathematics is really important. Many problems are solved with optimization processes. Often it is essential to understand numerics and how the accuracy changes in a certain processing chain of information. So therefore math is important. I commented already on the relation between computer graphics and visualization. I should add that also image and signal processing could be very helpful for visualization. For example, if you want to reconstruct data, it is quite useful to be aware of filters that extract features, for example, that find edges in the data and can emphasize them. Boundary emphasis techniques, this is called. Yeah? High performance computing could be quite important, in particular if the data is really large and complex. And yeah, some other disciplines are essential. Human-computer interaction is particularly important if we think about the interaction that we want to perform on visualizations. In HCI, there is a very good understanding of user-centered design and activity-centered design, so developing solutions that really fit to a certain group of users that want to do certain activities. 3D interaction is really at the intersection between computer graphics and HCI. Yeah, how to rotate, for example, with a mouse, that's a 2D input device, how to rotate a three-dimensional geometry, how to directly manipulate parts of a graphical visualization. That is what HCI can contribute. And in fact, there are a number of researchers that are really successful in both HCI and visualization. Yeah? And you may know that I also teach HCI, so also for me personally, thinking about HCI in depth is important for doing good visualization research. Yeah, what can be said about psychology here? It is particularly visual perception that is important, but also yeah, some more high-level activities like cognition and decision making. Yeah, if we want to support with visualizations leaders in industry, for example, in their decision making process, we really should understand decision making, yeah? The information that is used there and how it is interpreted. Design, design is related to HCI. Yeah, HCI involves a lot of design as well. Designers sketch a lot. They try to favor and support visual thinking. They try to create prototypes quite rapidly. That enables them to create many prototypes, or at least a number of them, and to discuss them and refine them before they would decide for a certain solution. Yeah, and that is, by the way, also the major contribution of Tamara Manzner that is described in her book so carefully, the role of design in visualization. Domain knowledge, of course, is very important. We have examples in archaeology, in biology, in engineering, geography, and medicine. In all these areas, you have experts that are trained, that have learned a lot, that have also seen many visualizations in their areas, that have some expectations, for example, how colors are used or some other line styles, drawing styles are used, and it is a good idea to employ this information when you design a visualization system. Yeah? So for example, a 3D visualization in medicine, there you are not completely free how you use colors for nerves and muscles and vascular structures, for example, but that is clear since centuries from anatomy textbooks which colors are used to show something. By the way, these are not the realistic colors that you would find in the human body. These are colors that have been used from didactical reasons in order to explain differences very well and to convey an overview on spatial regions. And in a similar way, there is this long tradition in cartography that is used in map design. Yeah, so this here really should make you a little bit familiar with this thinking in map design. Yeah, you have a base map and you have some additional maps of information, and the user may then specify which layers she wants to combine. In the old time, only the map author did this and he decided which static map is created. Nowadays, this can be flexibly combined by the user. Yeah, here you see this even a little bit more, which different information in this layered structure is available and can be combined. This is an example where a large pathway is visualized. And again, this is inspired by graph drawing as it was done in the early times manually. Yeah, so here a lot of chemical reactions take place, for example, in the respiration process, and it is shown which chemical structures are transformed in each other and how they are used in this large network of chemical reactions. Yeah, a few remarks on data sources. We have data that is computed. We have data that is simulated. I would say that occurs more frequently like computed data. And what also occurs very often is that we have measured data, for example, by means of various sensors. Imagine that the cars today have so many sensors, so many information is there and is used for autonomous driving or at least for assistive functions. So that could also be the source of the data. And then we have finally information systems like they are used in business, for example. If data is computed, simulated, or measured, the related visualization systems are typically characterized as scientific visualization systems. Whereas if the data is from information systems, that is called information visualization. These terms are a bit controversial and definitely not ideal. Yeah? It's not that this type of visualization is unscientific, and it's also not that everything that is done here is really scientific in a narrower sense. Yeah? Simulation is part of very routine engineering processes, and the way the data is analyzed could be also in a very routine way, not aiming at scientific discovery. Yeah? But these are terms that are used quite often, and therefore I want to mention them here. In addition to the given data, often it makes sense to use also new data that is derived from the data. So for example, you can summarize many pressure values, for example, by saying we always had a minimum pressure of this, a certain maximum pressure, and the median value or the average value is this one. Yeah? So one could say this is a kind of metadata that describes in an aggregated way our data. And imagine that we have really high dimensional data where we have 100 attributes. It could be interesting to see first a visualization that only shows for every attribute this summarizing high-level information. Sometimes it's also helpful to make operations on pairs of attributes. Yeah? So for example, we have one attribute A and another one B, and we are interested in the difference. We may be even more interested in the difference between the two than in the individual data of A and B. Yeah? Or we could be interested in the correlation between A and B. Yeah? If we have time-dependent data, then we are often interested in a baseline that is actually the minimum value that we always had, and we are interested in significant peaks, yeah, how strongly they deviate from the baseline. We may be interested in periodicity. To give you one example, many examinations have been carried out to understand energy consumption that changes over the hours of the day and over the days of the week and also over the seasons. So there are various levels of periodicity, and if you understand them, that helps to predict the energy consumption at a certain day and at a certain time of the day. And if you combine this with the weather forecast, then you know how much of this energy demand could be fulfilled by sun and wind, and you know whether you need other sources of energy in order to fulfill the demand for energy. Yeah. So, and then there may be other features that can be derived, like the gradient magnitude. Do we have, in a particular point of the data, large differences to surrounding values? Then we may have an edge there, a material transition, for example. Or whether we have low values, then this is yeah, a more or less homogeneous material. Yeah, to show an example from Tamara's book, yeah, here we have data on the import of a country and on the export, and here we have the trade balance, and that is obviously the difference between exports and imports. It's always positive, that's what we see here already, these lines do never intersect, yeah, but we see here more clearly how this trade balance decreased here in a certain area before it increased again. Yeah, derived data that can be very interesting and relevant to support certain tasks. This computation of derived data could be triggered by the visualization designer, that he really provides this with one button press, you get this information, or that a system is flexible enough so that the user has the option to trigger this process. Yeah, let me comment on the structure of the lecture. I will start with discussing with you visualization goals and principles, and then we'll go on with visual perception. There will be one lecture on data structures and formats that are used frequently in visualization, and this brings us to basic visualization techniques, namely to mapping of data to size, position and orientation, to various diagram types, to color coding, isolines and height fields. Yeah, these are really useful basic techniques. And I will provide one lecture on interactive visualization, where I will describe many topics, but for example, zoomable user interfaces, lens-based interactions, some types of interactions that are dedicated and tailored to visualizations and are quite useful there. I will provide one video lecture on uncertainty and the visualization of uncertainty. So first you have to quantify and understand the uncertainty, and once you have done this, you can think about how to visualize it. Then there are 3 video lectures on information visualization, 3 slide sets on information visualization, briefly structured along these lines here: graph-related data, multi-parameter data, line and icon-based techniques, and finally I will comment a bit more on visualization systems for information visualization. So then there will be lectures on indirect visualization of volume data and direct visualization of volume data. The last slide set that I have prepared is on flow and vector visualization, and it depends a little bit on how much time I spend on the lectures before, whether or not I will provide a video lecture that you should look at for the exam or not. In the last years I was not fast enough to make this lecture. Yeah, that gives you just a little bit more idea of what happens in the individual lectures. Yeah, so we discuss topics like spatial perception. Yeah, here you see shadow, for example, and maybe you agree that this shadow is quite important in order to understand where these spheres are in the 3 dimensions. That is just a sketch of visual processing in the retina and how the information is transferred via the optical nerve to the brain, where something is interpreted as an object, yeah, that is somehow similar to the real world object. We have yeah, visual cells, light sensitive cells, that are essential for getting this information. These are different type of light sensitive cells, and that is shown here. That means they have their maximum of sensitivity for different parts of the visible light spectrum, for different wavelength. Here you see that one line is straight, the others are all curved, and that becomes obvious immediately without attention. Yeah, so therefore that is pre-attentive processing. If I know something about pre-attentive processing, I can emphasize information in such a way that users will not miss it. Here, for example, the question is there any pair of parallel lines? That cannot be done with pre-attentive processing. Here you have to look at each individual pair of lines until you see, indeed, here is one. Yeah? So this is a kind of visualization that would not be useful for emphasizing something. Yeah? So that is just to give you an idea of what happens in the perception visualization. Yeah, then we want to discuss basic techniques like color coding, and I thought this quite old image actually shows why this topic is important. We see the same data displayed 4 times with different color scales. Yeah, this color scale here is continuous. Yeah, every different value here gets a slightly different color. This one, on the other hand, is a discrete color scale, or as Rogowitz and Treinisch say, a segmented color map. Here we only have 6 different values. Yeah? And that gives you slightly different information. Some subtle changes you cannot see here because you summarize a whole interval of values with one color. But for a basic classification, that may be even better. Here we do not use many different color hues, but actually only bluish colors. Yeah? And here is finally a color scale where we only have 2 values. That's actually a kind of threshold-based visualization. If the intensity value is above the lower threshold, that's approximately 120, and below the higher threshold, that's 170, it gets this yellowish color, and otherwise it's blue. Yeah? So that classifies the data somehow in 2 classes only. Yeah, here we see an isoline visualization, yeah, an animated visualization even. Color and isolines are used. That is a kind of visualization you would expect from weather forecasts. That is an example here from our research. So what you see here is the brain and the perfusion in the brain. That is how well different regions of the brain are supplied with blood. So you may imagine medical image data is acquired only if we have a patient. So this patient has a pathology, namely a stroke, Schlaganfall in Deutsch. Yeah? The patient has a stroke, and that becomes obvious here with this visualization, which combines color and height fields. Here is an area of the brain where the perfusion is very low, yeah, lower than in the other part of the brain. Typically, the brain is symmetric, yeah. So the asymmetry here tells you here is something wrong in the area where this yellow arrow points at, yeah. So here this perfusion is shown with height maps and color. Finally, you see data that conveys uncertainty. That is a so-called Kaplan-Meier plot that tells you for a certain therapy and disease how many patients typically live after 1,000 days, that's approximately 3 years, or 2,000 days, that's approximately 6 years, or 10 years. And the uncertainty is indicated by the width of this structure here, yeah, the distance between these 2 dashed lines. And you see that this one becomes larger over time. Why is this? Well, we started with many patients, and then we lose more and more patients, and at the end we only have a very few patients, and therefore, from simple statistic considerations, there is more uncertainty. So here, for example, we really see a step, and that probably means that just one person died, and so the likelihood for surviving more than 10 years is computed only for a very few remaining patients. Here's another example that was created for neurosurgery planning. Fiber tracts in the brain are reconstructed from medical image data with a quite complex processing chain, and the data only has a limited spatial resolution, so there is some uncertainty involved. The actual reconstruction delivers this blue surface here and these red lines. But based on the uncertainty considerations, it is indicated that actually this fiber bundle could be a bit displaced. It is somewhere inside these yellow circles, but it is not necessarily exactly here where the blue surface is shown. So that gives you a feeling of what could be done with uncertainty visualization. Yeah, this gives you an idea of what we will see information visualization. So here graphical, graph-based visualization is shown. We have connections between certain attributes, and if there are connections, we have lines in between them. That's a radial layout, a radial display. Some kind of edge bundling is involved to avoid that too many lines intersect each other. So that is an essential technique for information visualization. It's from Danny Holton et al., one of the leading researchers in this area from Eindhoven, and Jacques van Wijk is involved here as well. That is the supervisor, and he developed this technique, which is actually a hierarchy visualization. It could show you, for example, how the memory or the disk space on your computer is used in different directories where a lot of space is used. It's a type of visualization that is not intuitive. You have to learn this, but once you have learned it, it could be quite essential. Yeah. Surfaces from volume data, for example, with certain ISO values. Here, two ISO surfaces are combined. One represents the skin in the data and the other the bones. Here you see examples from our research on mesh smoothing, where we want to improve the quality of surfaces derived from medical image data so that they are smoother and easier to interpret. But on the other hand, we should not change the surface too much. We must be aware that the accuracy, of course, is important here as well. This gives you an idea of volume visualization, so direct volume rendering here. No intermediate representation is computed, but the data is directly mapped to colors and opacity with the so-called transfer function, and this may lead to very impressive visualization. And Timo Rupinsky was one of the researchers who really pushed the limits forward of the degree of realism that could be achieved with volume rendering. Yeah, and finally flow rendering. So here you see streamlines that indicate blood flow as it was simulated in an area where the vascular structure is ill. And physicians want to understand the flow. They want to understand whether there are some vortices where the flow goes around. And that could be shown with this type of visualization quite well. The color, by the way, here indicates the speed of the flow, whether it's faster or lower. Here we see a visualization that is even older. And yeah, the more it is surprising what could already be achieved at this time. That was based on a simulation of the flow around a car. Yeah, maybe you recognize that this is an old BMW car, and the flow here was simulated and visualized, and that helps you to understand if you change something in the geometry of the car, how would this change the flow that affects the consumption of energy. Yeah, so virtual wind tunnel experiments could be carried out here with appropriate computation, simulation, and visualization. Yeah, that was what I wanted you to tell in this very first video lecture to make you aware with what happens. In the following, I want to make video lectures typically 1 hour long. So typically I split one slide set into video lectures. I will always give a list of all the references that I have used for preparing this video lecture, and typically I'll also emphasize some of them. I emphasized and mentioned already all the books that I recommend to you, so I don't want to repeat this again, but I want to emphasize 2 articles that I have mentioned in quite some detail. On the one hand, Chris Johnson's list of top scientific visualization research problems, short paper, 5 pages only, very high level, easy to understand, but with a lot of wisdom. And since this already, although this is already 16 years old, many of these research problems are not fully solved and are still interesting. And the second, yeah, I called it self-reflection type of paper I wanted to emphasize is this report from McCormick, DeFanti, and Brown, Visualization in Scientific Computing and Computer Graphics, which appeared in the ACM SIGGRAPH. Yeah? And here for completeness, just the other publications that I have used for this lecture. Yeah, with this I'm at the end of this first video lecture and want to thank you for your attention.